Thank you all for joining us today for this mini symposium on the U.S. and International Earth Observation from Space Program of Record. Thanks also to the Keck Institute of Space Studies and the JPL Center for Climate Sciences for sponsoring today. We have some great speakers that'll help us learn more about the NASA, NOAA, USGS, and international programs of record. As you can see on the slide here, we are recording the talks today. We will post them to the websites that are listed, and we'll come back to this screen at the end so that you can copy down the links if needed. Before we dive in, I'd like to introduce Dwayne Walliser. He is one of the three co-chairs, along with Betsy Weatherhead and Tapio Schneider, of the KISS study that you'll hear a bit about today. Dwayne is the Directorate Scientist of the Earth Science and Technology Directorate at JPL, and he presently serves on the National Academy's Board of Atmospheric Science and Climate and the Committee for Earth Science and Applications from Space. Dwayne.
Thank you, Stacey. Thank you all for attending today. I'd like to provide some context for today's symposia, and please bear with me as it's prepared written material. It gives me the best chance to be as precise and complete as possible, as I'd like to be, and as compact as I need to be to stay on time. The issue of continuity of satellite observations for climate change science and projections, as well as for mitigation and adaptation decision support, is warranting increasing attention. While there's an excellent and established framework across our government and commercial sectors that leverages and contributes to a working international framework for the weather enterprise, there are other dimensions of observations that lie outside this system needed to support climate change science, benchmarking and monitoring of mitigation measures, and decision-making to foster societal resilience and sustainability. This includes measures of the water, energy, and carbon cycles, as well as their extremes that can have significant environmental impacts and associated socioeconomic consequences. It's a very opportune time, particularly in the US, to be raising the level of discussion around the topic of observation continuity as it applies to satellite programs. Many of you know that in the coming couple years, the fantastic satellite-based climate records initiated by the EOS program, namely the Aura, Aqua, and Terra platforms, will be coming to an end, of which a number of key records do not have any immediate or obvious forms of continuity. Moving forward as a community, this is a situation that I suspect we'd like to shore up and not continually find ourselves in. A particular note is the midterm review of the 2017 Decadal Survey is expected to start up in the coming months, and it is anticipated that this topic will be raised and examined in that review, with a further expectation that the 2027 Decadal Survey will seize on it as a critical topic. Community sentiment and guidance on this topic has tremendous value and has a twofold benefit. First, the satellite segment of our Earth observing system is a huge piece of the aggregate and interagency Earth science and application pie, literally billions of dollars in investment across multiple agencies. Second, the ramifications of having an optimal versus suboptimal observing system for climate science monitoring and projection is almost immeasurable when it comes to societal benefit. Thus, events like this and others that have the potential to help gather and infuse community guidance on this topic can likely have tremendous impact for the country and possibly globally. With this motivation in mind, Caltech's Keck Institute for Space Studies, or KISS, and the JPL Center for Climate Sciences, which is co-directed by Joao Teixeira and Graham Stevens, are hosting today's mini symposia. This builds on a sequence of mini symposia initiated and planned by the JPL Climate Center that are intended to raise awareness of the importance and value of satellite climate records, with the first of these symposia having been held in April on climate and radiation monitoring. Today's symposia and another planned for July 15th, focusing on commercial and non-government players, is intended to continue this thread, but also support and provide important background information for an upcoming KISS study on this topic that will commence in August and conclude in the fall. This study, which includes a mix of 30 members of our community, including virtually all of today's speakers, has a goal of discussing this topic in earnest over the course of 2 in-person study weeks, culminating in a report of findings and recommendations on the topic. If you want to learn more about this study, please Google the words Caltech and KISS, and you should be able to quickly zero in on it. With that as background and motivation for today's symposium, I'd like to hand it back to our MC, Stacey Boland, who is a senior system engineer at JPL, has worked on a number of Earth science flight missions, including RapidScat, OCO2 and 3, and more recently, the upcoming Earth Venture mission Maya. Moreover, Stacey served on the steering committee of the 2017 Decadal Survey, and thus is particularly well suited for her role today. Thank you, Stacey.
Thank you, Dwayne, and thank you so much to all of our speakers today for helping us learn more about the programs of record of NASA, NOAA, USGS, and the international community. I'm going to introduce our first speaker in just a moment, but I would like to just say that we will hold questions until the end. We will have time for a moderated Q&A session and hope for a good discussion after the talks. You're welcome to use the chat feature, or we can also use the hand raise feature when it comes to that time. With that, I'd like to introduce our first speaker, Waleed Abdalati. He is the director of the NOAA University of Colorado Cooperative Institute for Research in Environmental Science and professor of geography at University of Colorado. He served as NASA's chief scientist in 2011 and 2012 and is co-chair of the 2017 Earth Science and Applications from Space Decadal Survey. Waleed.
Let's see, can you see this?
Yes, perfect.
Okay, great, thank you. So thanks for the opportunity, and of course, thanks for the effort. I appreciate your putting this together, calling us together, because this really is a critically important topic that I think we all appreciate. But to make progress is really going to require a community effort. So let's see there. So I'm going to start with this slide, which I know probably all of you have seen, but it's an incredibly powerful slide because it tells a story. It tells a story of where we stand with respect to NASA's space-based Earth observations. It tells a story of where we've come from. It tells a story of where we're going, and it tells a story of partnerships. And when I look at this, I'm really amazed actually at all we as a community have been able to do and all we have to look forward to. But there are challenges, and that's essentially why we're here. And for people who aren't familiar, the blue missions are in extended operations, the green missions are in current operations, the orangish ones are in implementation phases, and then the yellowish ones are out into the future, but that we currently are planning for. So I'm gonna mention, when it comes to those blue missions, we have them because one, outstanding engineering and project management has allowed these to be produced to last beyond their design lives. And two, because NASA has and other agencies have chosen to dedicate resources toward their extended operations. And the process by which that's done, I think most of you know, is through the senior review, whereby mission leaders and managers come forward and scientists come forward and make the case for investment and resources into these continued operations. And I think we all intuitively know that it's cheaper to keep a mission going than to build and launch and operate one in the future, but it does require substantial resources. So something has to be given up to maintain these capabilities. So the next one is scheduled for 2023, and the one after that, 2026, where some of these green missions will be under consideration, at least in 2023, and by 2026, maybe some of those orange missions as well. I'm going to talk briefly right now about the Earth System Observatory 1, 2, 3, and 4, which does not have a launch date, but these came from the Earth Science and Applications from Space Decadal Survey. These were identified as designated observables. Clouds, aerosols, mass change, surface deformation and change, and surface biology and geology. This was something that the committee, in consultation with the panels and with huge amount of input from the scientific community, identified as variables that needed to be specifically identified as having dedicated observations toward them. So they were referred to as the designated missions. They're underway, or at least efforts are underway to develop these or make progress on these. This is just summarizing where these currently stand, when the MCRs are scheduled for, and the one in study phase currently. And I think it's worth mentioning that NASA is in the process of setting, or has pretty much set up, an independent review board to review their plans from both a scientific and implementation perspective for these, to review the architecture for these upcoming missions. That effort is just about to start and should be done, I would imagine, sometime in mid-September. It's going to be a quick turnaround and will inform NASA's next steps in terms of kicking off these missions. So stay tuned for that. I highlight those because in the beginning we had Aura, Terra, and Aqua, or Terra, Aqua, and Aura in chronological order. And as we look to the future, sort of the designated missions that we see coming down the road are these 4/5, depending on how you count them. The aerosols and the cloud and climate processes really are integral to work with one another. So stay tuned for effort on that front. But I'm going to go back to the beginning. And what I mean by the beginning is the beginning on this chart of what is currently operating, not the beginning of the whole Earth observing system. And just focus briefly on Terra, Aqua, and Aura, because they comprise the core, the flagship missions of the Earth observing system, or for those my age and older, the mission to planet Earth. And I'm going to just call your attention. We all like to think in terms of instruments and missions because it's what we're familiar with. They're the capability, they're the tools by which we make the measurements. But for the purposes of continuity, I just want to call your attention to the last column here. Focus a little less on the first and more on the last. I'm not going to read through these. You are all probably more familiar than I with certain elements of this. But I did want to put this together just for reference. We've got land surface characteristics, clouds and radiation balance, aerosol and cloud amounts, heights, coverage, extent, surface cover and type, surface temperatures, vegetation, water, etc. And in the case of Moppet, specifically focused on pollution. On the aqua instruments, atmospheric temperature and moisture profiles, trace gases, clouds and radiation balance components, allowing us to calculate or determine the radiation balance, precipitation, cloud, water, vapor, ice, snow, soil moisture, sea surface winds, SSTs from the passive microwave capability, and also another MODIS instrument, as was the case on Terra. And Aura, more geared toward the chemical makeup, total ozone and pollutants, atmospheric composition, the chemical state of the troposphere, which was TESS, which is its life ended in 2018, and then again MODIS. So these are, again, they comprise the core. They are 20 to 22 years past their launch dates, well past about 15, 17, 18 years past their design lives, still operating in most cases and still providing important information to us. But these are going to be subject to the senior review for continued operation. And again, as flagship missions, as the core observing capability, getting through senior review in the past, I'm sure I'm oversimplifying to those who've gone through it, but it's been pretty straightforward. When we look to the 2023 senior review, what you see in the colors here are different stages in a mission that has been extended from the extension of the mission to the final processing. And really what I want to call your attention to is on the left, the in guide with the current resources, when science ends for each of these missions. And on the right, the over guide, meaning if the missions are extended, successfully pass through the senior review, when we can expect operations to continue until. So the point here is twofold. One, there is an opportunity when these missions work to continue those operations. But two, it takes resources. And when we dedicate resources to these kinds of things, it draws resources from somewhere else. And this is the challenge that NASA continually struggles with and will continue to struggle with as we work toward continuity of observations. I guess, you know, it's a trade-off between important sustained measurements and innovative new measurements. We really need both. If any of us were in charge, there'd be plenty of money for both. I mean, in charge of OMB, not in charge of the agencies, because it's a higher authority than that, but there simply is not. So with that in mind, I want to focus on sustained observables. You're going to see a lot of charts, and I'll say this up front. You know, I'm not going to go through every line and every chart in my presentation. They're more for the record. But this chart and the next one, I did want to focus on the observables that are in pretty good shape for the coming decade, or close to it at least. And that's not to say there aren't some challenges, but this is areas where we can look, where we look and we see mission capability to continue observing these parameters. So one is high resolution land cover, most specifically with the Landsat series, which you'll hear more about, I'm sure, from Tim. Radiation budget, a number of sensors. We've had a great run with the CIRES capabilities. And by the way, this middle column, or the second column, is past and future. It's not intended, it's intended to capture the kinds of things we've used to look at these parameters. The third column is the date through which we're confident that we should have capability. So, and I'll also say, if you look at my disclaimers at the bottom, I'm oversimplifying. I know when I identify an observed parameter in this left column, it's not the way I'm too broad, and it's not the way it's needed for all kinds of applications. So I'm sure someone is looking at each of these elements and saying, well, you know, particularly ozone, you know, there's stratospheric, there's tropospheric, as a pollutant, as UV blocking. So I understand that I'm oversimplifying here, but what I'm just trying to point out is there are certain observables that we have identified that investments have been committed to for continuing observations for a number of years going forward. And then number three, on the launch dates, for the NASA piece, I just took expected launch date and added 5-year life. As is often the case, fortunately, they will likely go longer, but as is sometimes the case, unfortunately, they may not last as long. So this is a list of some high resolution land cover, radiation budget, brightness and spectral irradiance, sea surface temperature, land characteristics, ice and snow, at least in the visible, you know, detection of and spatial extent, sea surface height, ozone. And then this chart is the same idea, same headings, but this focuses more on the decadal survey designated mission. So I'm going to just take it as a given that you've all read the pure gold that is in the decadal survey, and understand what all of these refer to. But I do think I just wanted to highlight that what we've identified as designated observables and what NASA is working toward, with, they say 2028 to 2030 launches. It will, I think, in many cases be later than that. But cloud structure, height, optical properties, and precipitation state, the aerosol properties and profiles, and their relationship to clouds, changing mass distribution, the GRACE type satellites, surface deformation and change, the INSAR type satellites, and Earth surface biology and geology, the MODIS VIIRS type instrumentation that has been so successful over the years. So missions in the NASA program of reference. So now I'm flipping here. I said, let's focus on the observable. What have we got that we can look forward to, that we can plan for and plan toward? Now I'm going back to missions, and the observable is in the second column, because it really is these missions that are going to determine how long we have these observing capabilities for. So if you just go down this list, it pretty much is not pretty much, it is the order in which you saw them in that spiral in my first slide. These are on extended mission, I think up through Cygnus. And the reason I have greater than or equal to 2023 is because that's when these will be subject to senior review. By then, the GRACE follow-on, even though I think it's currently in its current operations mode, by 2023 will be past its design life. Moving forward in time, these missions also will presumably be subject to senior review. Well, ISAT-2 will, the Sentinel-6, Michael Freilich, the design life carries it through 2025, so I would expect it to come up for senior review in the 2026 review. Now, when I change here to green, these are missions that are planned. They have not yet been launched. Some are very close to launch. Some don't have launch dates yet, but these are missions, and the date I put is not the life, when we expect the earliest end of life to occur, but these are launch dates. So you can look at these and determine most have 5-year design lives. Some are shorter, however, but this is just to give you a sense of when they're going to be put into space and when they're going to be launched. So there's just way too much here to walk through. Again, I'm going to assume these charts will serve as a reference for people in the future, and we simply don't have the time to talk about this stuff now, but I just wanted to put it out there to call your attention to it. You can reference it later. And it may well be I've gotten a couple of things wrong. I don't think so. I tried to do my diligence, but if when someone looks at these and sees a mistake, please call it out. Either today in the Q&A in the panel session, if there's something glaring, but at least write to me, tell me, hey, Waleed, you missed this one, or you got this wrong. Because I do think it's important to have a program of record to pull together. I know this was a huge effort in the decadal survey, and I've gained a new appreciation for Stacey for having done that in the decadal survey for all space-based missions in the program of record. My efforts for the NASA were pretty substantial. So there may be some inaccuracies here. I don't think so, but please call them. I invite you to call them out if there are. So going from blue to green, And then more green. I'll pause here and just let you read the mission that's most personal to you. But again, this is more for reference in the future than it is for discussion right now. And then moving to those on the International Space Station, again, blue is what's currently operating and the expected life post if it's supported past the senior review. And then green are the ones for which that have not yet been launched, but are expected in the future. And then I lost it. Okay. And then I can't talk about the program of record without bringing in the fact that there are going to be other elements in the program of record going forward, but that depends on what competition produces. Certainly, we've had the Earth Venture line in the budget, which has produced some real innovation, and I'm delighted, that being part of the decadal survey, we were able to put forward the recommendation, and it was accepted that there also be an Earth Venture continuity budget line to come up with low-cost ways of effectively measuring variables that really need to be sustained. But that's limited. Another deciding factor in the program of record is what's going to be successfully proposed through the Earth Explorers. And so that was another line, budget line that we had recommended be put in. And in Earth System Explorers, NASA is expecting to solicit 2 this decade. We identified topic areas that will guide the solicitation for those. They're shown here. I won't read them to you, but between this and the innovative ideas that are going to come forward through the Earth Ventures program, there's a lot of unknowns, but really good unknowns in what will be the future program of record just a few years from now. But I did want to call that out because this is going to influence what comes forward and how we think about the future. Let's see. So I'm going to come back to this slide here, and I just want to call out on the middle of the right side, the JPSS instruments. You'll hear a reference to them coming up shortly as well. But this is interagency partnership that is going to carry forward a lot of the capabilities. If you go back to my chart here under sustained observables, you'll see JPSS appear a few times because it is really going to be carrying forward some of these critical climate observations. So I guess the last thing I want to touch on here is we've had the decadal survey recommended decision rules for absorbing budget challenges. Now, we all know budget challenges arise from different sources, but one of those sources that presents budget challenges in a good way is long missions, as I mentioned. So when we have the senior review and we choose to extend missions, it does have implications for what we're able to do going forward. But there are also budget challenges where NASA is not provided with the resources it needs to execute the program that it's been charged with executing. We worked diligently in the decadal survey to ensure we were working toward planned budgets as opposed to aspirational budgets. In the first Earth Science decadal survey, I understand and support that the idea was working toward aspirational budgets, but the reality that panned out suggested otherwise. So when we did ours, we worked towards planned budgets or current budgets adjusted for inflation. But the simple fact is challenges arise. There's always not enough money as you thought you had. So we came up with these decision rules for absorbing budget challenges. And the reason I'm showing them here is because they will have implications on the program of record going forward. The first is delay the large missions. We prioritized competition. The second is delay medium-sized designated missions, unless we felt all the designated missions were important for continuity or making the most necessary observations going forward and ensuring that that could be done. But you can imagine if, for example, the GRACE follow-on mission lasts as long as the GRACE mission did, then perhaps the mass change mission need not be launched as early. Again, this is how do we deal with budget challenges? But if continuity is threatened, the cadence of the medium-sized competitive missions, that being the explorers, should be reduced, but to no fewer than 2 competitions in the decade. I believe that that is the plan, that there will be 2 Earth Explorer opportunities in the decade. So already managing some budget challenges. We felt that the budget for ventures was as lean as it could be, so should not be reduced by more than 5% from the historical averages. And if all of these can't handle it, go to CSAS. Ask the academies for guidance and advice. So with that in mind, I just want to finish with, I think, some optimistic statements. As a community, there is so much in place. We've been fortunate that the success of these missions has been ongoing. There's so much to look forward to. There's a lot ahead, a lot of great, exciting measurements and capabilities that lie ahead. And I think we should all be excited that those exist and that we'll have the opportunity to work with those. We have a lot to be proud of. When I think of the challenges the community has faced, and from the beginning, since Mission to Planet Earth was first put forward, and there was some significant budget increases in its early days of implementations, but challenges in the decade that followed. I think we've worked well within the challenges. I think we've been successful advocates, and I think we should all be proud of what we've accomplished, what we've been able to work out, what we've been able to work with, and what lies ahead. But as a community, we have a lot more to do. And this study, this KISS study targeted at sustaining or managing to achieve continuity and climate measurement capabilities is part of that effort. I think it's a big part of that effort. But we as individuals have a responsibility, one, to support such efforts, to gather, to advocate, to come up with creative ways to accomplish the objectives we seek to accomplish in an environment of limited resources, and garner support for the kinds of things we're pursuing. But at the end of the day, I think we've got a lot to be proud of, a lot to look forward to, and a lot of, I think, great work ahead. So with that, thank you. I appreciate your time.
Thank you, Waleed. As mentioned at the top, we'll save questions for the end during the moderated Q&A. So now let me introduce Michael Bonadonna, who serves as the Department Chief of the Systems Architecture and Requirements Division in the Office of Systems Architecture and Advanced Planning of NESDIS NOAA. He served as the Federal Coordinator for Meteorology, managed the National Space Weather Program, and commanded and directed operational weather services to the military forces around the world. Mike.
Hey, good afternoon. First, the sound check, and can you see my slides?
Yes.
Okay, very good. Good afternoon, ladies and gentlemen. I appreciate the opportunity to speak with you this afternoon, give you an overview, an introduction to the National Oceanic Atmospheric Administration's National Environmental Satellite Data and Information Service, NESDIS. As mentioned, I am working in the systems architecture and requirements division within NESDIS in the Office of Systems Architecture and Advanced Planning. First, as a space agency within the federal government and NOAA's space arm, we are very proud to show our baby pictures. Here, our last satellite launch was DOST, which became DOS 18, which became operational, launched on March 1st of this year. And on the right side, you see the full disk from its position in geostationary orbit. It will be drifting. It is currently drifting to its operational position over the Pacific Ocean presently. So just let me preface my presentation by saying that this is an overview briefing. For the end of the briefing, I have some program of record information with links to extensive details that I was planning on using when we get together in August, roll up our sleeves and dig into this. But I thought it was very important that that we had the opportunity for you to get an overview of how NESDIS operates, what it's responsible for. And here on this slide is a depiction of data fusion that takes place. NESDIS is a leading source of environmental information for the United States, provide operational weather, climate, hydrological support for the nation. Here you see a combined image from our geostationary asset. Those our system goes 16 with its two instruments overlaid in its baseline imager and global lightning mapper, GLM global lightning mapper. This is a new capability in the GOES-R series, and we are already making great operational use of it. The research community is also latched on to the importance of lightning combination of severe weather, tropical weather in this case. So we have a global perspective. This our low Earth orbiting satellites capture the entire Earth twice a day each, and provide a plethora of data sources and data types that we fuse together and provide as products for our customer base. Truly integrated digital understanding of the Earth, and more so with the advancement of machine learning and artificial intelligence, the applications for national the numerical weather prediction, we just continue to be on the forefront of science. Well, we've been doing this for quite a while, going all the way back to the early 1960s when where the satellites were an early focus in the early space program. Capabilities continue to advance. Chart is organized, so the top of the chart are the geostationary assets, and lower part of the chart depicts the low Earth orbiting assets. And in combination, as the capabilities continue to evolve over the decades, a truly global view, integrated, fused understanding of the Earth environment has been obtained. This goes into the future a bit, talking about our upcoming programs, and I will describe those later in the presentation. And I will be moving through the slides fairly quickly, since I do have a number of them, but you can look them up at your leisure. I find this slide to be particularly useful. This is the various roles and responsibilities of the national space endeavors that NOAA partners with. And NASA, NOAA, USGS, and Department of Defense all have their specific roles to play. And the combination of our capabilities and how we work together and how we take advantage of each other's particular assets is very important. In my last role as the federal coordinator for meteorology, we looked at making sure that all of the federal agencies work very closely on this in the space and satellite arena. Now, I'm not going to read through this chart, but a very important relationship to call out is the NOAA NASA relationship, which NOAA provides the operational support. NASA focuses on the research effort, but there is great synergy between the two. And NASA also serves as the acquisition arm for acquiring the NOAA satellite systems, primarily the geostationary and low Earth orbit satellites. Our other partners with the USGS, you'll hear from Tim Stryker later in May, and the Department of Defense can also contribute greatly with their specific capabilities as well. At the core of our NOAA's mission is to inform the nation from an economic preservation of life standpoint. The chart on the left side here depicts some of the billion-dollar weather events that have taken place over the years, and a tremendous increase in that upward trend in those billion-dollar impacts over the years. NOAA's role in placement within the Department of Commerce focuses on helping the communities, particularly communities that are disproportionately affected, mitigate and prepare for both weather and climate impacts. I'm sure you all know this, but often when this slide is presented in non-technical terms, people don't understand that some 95% of all the data used in the weather forecast models come from satellites. And it is a very important effort to take the best advantage of those satellite observations that we can. We operate, of course, 24/7 in acquiring the next generation satellites to observe the Earth. The real focus, though, is on the data, imagery, and the products. And I have a few slides on that later. That's what drives the train for an operational organization like NOAA and NESDIS. Of course, our data are also extremely useful in advancing science and for oceans and industries. Here are some of the applications that we've had over the years. So I'm not going to read down the chart here, but things like coral reef rock, harmful algal blooms have become an extremely important impact to the blue economy, oil spill and detection, and NOAA provides search and rescue information from their satellites to the nation. In the area of crisis response and economic recovery, a couple of things to keep in mind is that chart on coral reef watch and coral bleaching. Very significant impacts around the world, and the NOAA satellites, along with our partner organizations, provide the data to do analysis like this. The fires in the western United States have been a particular emphasis within the federal government in the last several years, and many efforts are taking place to look at, mitigate, and try to prepare for this increasing devastating problem. From the SARSAT, the Search and Rescue Satellite Services, great number of rescues every year. Some of them are listed here. Just from an organizational standpoint, our Administrator Stephen Bolts and our staff for reference. And here are their driver's license pictures. No, not exactly. You looked at that. Dr. Bolts is our assistant administrator. Mark Parisi, our deputy. Mr. Dan St. Jean is currently our acting chief for advanced system planning and architecture. So he's my boss. And this is distributed around the country and around the world with their number of offices. Primary campuses are in Silver Spring, Asheville, North Carolina, Stennis Space Center, and Boulder, Colorado. Some of the other points that you see on the map are locations for antenna downlink services. Again, I'd like to come back to the idea that key customers and partners are really how we get things done. Our key partner agency partners, as I mentioned, NASA, United States Space Force, the United States Air Force in the interagency realm. Internationally, looking forward to the presentation coming up later today on the international efforts that are going on. NESDIS plays a key role in WMO, CIRES, CGMS, GEO, USGO in particular, and some of the customers that we serve. And we also have long-term working relationships with industry and commercial providers. Of course, working through NASA as our acquisition arm for all the companies that are developing the systems that we use. But at the bottom of that chart is somewhat new, and we'll be hearing more about this, I'm sure, in our next symposium on commercial services environmental data. NOAA NESDIS is taking particular interest and has been funded to leverage commercial capabilities that are coming on, particularly GPS RO for atmospheric sounding observations and space weather data as well. On the international front, here are the groups that I mentioned. The Earth is just too big for one agency to tackle on its own. So in order to leverage the capabilities from around the world, we have a very strong international partnerships with the organizations that you see here, in particular the European and Japanese meteorological agency and Canada. So this starts to get to some of the questions that were particularly in program of record. So you would have hoped that the roughly $1.5 billion a year organization would have a relatively steady budget over the years, because most of the funding that is needed to prepare for and operate our satellite systems are tied to the major satellite programs. It's all tied to the phasing of those programs, and that's why you see a rise in the last decade, somewhat down a bit, but predicting another rise coming forward. It's really quite tied to the systems that we're pursuing. And this little button down at the bottom that says NOAA Blue Book is what we'll be talking about when we get together face to face in Pasadena. That gives all the gory details about the NOAA budget, how it's being spent, what the plans are. But there's not time today to delve into that. So let's talk about the program of record a little bit. First, it starts with the funding mission requirements. The office that I work in is a key driver of requirements gathering from a very diverse user community, documenting that and helping to drive the programs. 4 pillars of our next generation satellite observations. This has been somewhat reorganized in the last several years, and I think to a very good advantage. Low Earth orbit assets are more than just the JPSS spacecraft. Going forward, we're looking at the distributed low Earth orbiting constellation to take advantage of small sat, microsat technologies. On the GEO front, of course, we have a program of record for the GOES-FAR satellite series, and then GEO-XO, which will be the follow-on system. But looking at it from a user perspective as well. Space weather is not new, but it is somewhat new to NESDIS. We are taking a very substantial effort looking at space weather, developing the assets for both GEO, LEO, and extended orbits, L1, L5, we'll talk about that a bit. And underpinning all that, we'll have common ground services which provide the secure ingest for all the formats and serving the different partners. And this is moving to an integrated cloud AI machine learning approach as over the next several years. On the low Earth orbiting front, you mentioned the JPSS spacecraft and our partners with NASA and Eumetsat in Europe and JAXA. So some facts here. Think of the low Earth orbiting satellites as providing the global high resolution coverage that we need both in terms of imagery and soundings. Very useful, very critical to numerical weather prediction models. The geostationaries have traditionally operated two, one over the East Coast and one over the Eastern Pacific Ocean. Those East and West as they've been called. And here are some of the fun facts that are using data from GEO. The image that you see in the upper right is a combination again of that goes lightning mapper and the fast baseline imager. And this particular one was the longest continuous lightning strike ever imaged. That is one system of a lightning strike. And space weather. Just in our context, there's little impact of space weather on the climate, but there's some. And the Deep Space Climate Observer does carry two NASA instruments that are particularly focused on climate issues, but it's primarily the space weather asset for serving that aspect of our business. The follow-on system, space weather follow-on, is in preparation currently, and then the system after that, and we're referred to as the Space Weather Next program. So this is our big overview chart of who's doing what in near Earth orbit and geostationary ring, and how we partner with them. This particular chart just again reemphasizes the point that we focus on products and services, innovation in the overall production and development of our system. It's not about the cool space stuff. It's not about the amazing ground systems. It's how we are serving our customer base. Our Office of Satellite Product Operations, our 24/7 operation, manages the complete fleet of spacecraft that we have and provides partner services as well. A very, very, very long list of operational products and service mechanisms are controlled from OSPO. You can see here on the right side some of the ground systems that are the STAR, our Center for Satellite Applications and Research. This is where most of the algorithm work is done to take the ones and zeros coming down from the spacecraft and turn them into usable products. NCEI is really a national treasure. It is one of the largest warehouses for environmental information in the world. They have extremely capable systems to be able to use a vast variety of data sources to produce value-added products and services. And when we get into a conference together, we need to explore this aspect of NESDIS quite a bit. Here's our timeline for the current into the future, and where we'll be heading with our systems. The GeoXO program coming on after the completion of the GOES CIRES satellites, and the development of systems beyond JPSS. My office, the Office of System Architecture and Advanced Planning, we focus on the 2030 to 2050 time frame to start moving all of our systems in that direction. So I think that's customer, improvements to customer, always working. The NESDIS Reimagined focuses internally on our workforce diversity, equity, and inclusion aspects. And that is what I have. There we go. A picture from our East satellite in gray night and true color. So we'll save questions for later. And thank you for your attention.
Thank you, Mike. Next up, we'll have Tim Stryker, who is the Chief of the Outreach and Collaboration Branch at the USGS Department of the Interior. In his role, he's concerned with national and international Earth observations policy and processes, research to operations processes for civil Earth observing satellite systems, and public-private partnerships, particularly as these relate to NASA USGS Sustainable Land Imaging Program, the Committee on Earth Observation Satellites, and Group on Earth Observations. Tim.
Thank you, Stacey. And I'd like to thank the Keck Institute, Caltech, JPL Center for Climate, Betsy, Dwayne, and Tapio for your leadership of this study, and Stacey for emceeing, and Wingsy for your liaison and support. I am very appreciative of the opportunity to be serving on this study team. I really look forward to learning a lot from each of you. USGS is, in fact, an Earth observing space agency. Not many people recognize that. Remotely sense many users. So, for this study's purpose, our program of record is, rather narrowly defined. In that it's focused on the Landsat missions and related partnerships. We don't operate multiple missions a la NASA and NOAA, are much larger sister agencies in civil Earth observations. But it is a very substantial, I think, commitment and program of activity for the USGS in terms of its size and its budget. And our program, works very hard to make satellite land remote sensing observations a worthwhile investment for USGS science in support of our parent department, the Department of Interior's objectives. And we want those to complement as best they can, other data sources, other observing systems that USGS operates, and I'll speak to those a little bit as well later, as well as the numerous external data sources that we leverage from NASA, NOAA, and our many international and commercial partners. So for those of you who aren't aware, USGS is one of 9 bureaus with structure. Leadership is shown here. Current secretary is she's a former congresswoman from New Mexico. Comes from the West and is a long practicing attorney on water resource issues. And just most recently here for currently our associate director for natural hazards. You can see the structure and organization here and under the water and science.
Apologies for the interruption, Tim. Your audio is breaking up. Are you able to move closer to the microphone or turn off noise cancellation?
Yes. Can you hear me better now?
Yes, thank you.
Okay. I'll just go with that. Please let me know, Stacey or others, if you can't hear me. So you can see the structure here and kind of the roles and responsibilities of Interior. Our department protects and manages the nation's natural resources and cultural heritage and provides scientific and other information about these resources to the public. It's responsible for honoring U.S. trust responsibilities and special commitments to American Indians, Alaska Natives, and affiliated island communities. And the Interior Department plays a central role in how the United States stewards its public lands, including their ecosystems and their water, mineral, and energy resources, how the U.S. maintains and increases environmental protections, how we support environmental justice in underserved communities, as Mike notably mentioned, in terms of oftentimes environmental problems, weather disasters, other things tend to affect disadvantaged communities more than other communities in our country, and also honoring our nation-to-nation relationships with the tribes. See here, in terms of the department's role, we're responsible for managing 20% of the U.S. landmass. That equates to about 480 million acres of public lands, most of them also 700 million acres of subsurface minerals and 1.7 billion acres of the. Of course, there are lots of demands, recreational, conservation, resource utilization, many interests to be balanced and sorted through. So the Interior Department has 70,000 employees across the nation, and interestingly, 280,000 volunteers. So I guess like the Army, it's not just a job, it's an adventure. Lots of people continue being involved with Interior due to our mission across the United States. And so you can see the DOI and its bureaus listed here to the right. And you can see our role here at USGS. We're one of the 9 bureaus. Our enacted budgets for 2021 and 22. And our role within USGS is to provide sophisticated and objective earth science to support DOI's many missions. So, and at the map here, you can see all the public lands and locations, historic sites managed by DOI across the nation. And so DOI relies on USGS science in terms of mission and vision statement. This is USGS's right here. It was actually adopted, promulgated in 2021 after a 2017 initial gathering and a lot of work among a USGS Council senior scientists advisors. And focus really here now is, with the maturity we have in landscape scale and land surface observations, we're really looking to orient ourselves around an integrated kind of Earth system research, monitoring, and a predictive capability ultimately. So it's truly intended to be a system of systems approach, where in each of our scientific and technological disciplines can contribute to a greater whole. And that's, of course, in close collaboration with many other federal agencies, external partners at the state and local and international level, and commercial firms involved in science and Earth observations. So the idea is to really span all the scientific boundaries of Earth system science and invest more in data integration, high performance computing, artificial intelligence, modeling, analytics, lab facilities, visualization, and various decision support tools. Ultimately, our objective is to deliver actionable environmental information in the form of integrated observations, scenario planning, and predictions of the future state of Earth systems. So you can see there's a lot of commonality with NOAA in terms of operational monitoring, forecasting, and analysis. And we learn a lot from NOAA and other U.S. partner agencies in conducting this. So without getting into much more organizational detail, I'll just let you know that USGS is organized into 5 different mission areas. Those are ecosystems, natural hazards, water, energy and mineral resources, and core science systems. And there's more detail on those in the backup slides. I've got a lot more detail in the backup slides for those who are interested, and we can talk more in Pasadena about that. And our program, the National Land Imaging Program, is located within the core science systems mission area, where most of our remote sensing and geospatial data is managed and systems are operated. So moving on to our science strategy, you can read more about our approach in the science strategy. Very integrative. We're seeking to move away from traditional kind of separate academic disciplines of geology and hydrology, cartography. One good example we like to use is with regard to fire science and the importance of wildfire in the United States and many other countries these days, in terms of bringing different components and science experts together with different types of data, and envision how existing databases and observational capabilities, information products, everything from Landsat derived information to aerial LiDAR to hyperspectral aerial remote sensing, debris flow hazards, modeling, mapping, how all these can be brought together in a more advanced computing environment to inform wildfire management before, during, and after fires themselves. So I have a brief slide here on USGS by the numbers. You can see we all then grew with the US itself and kind of westward expansion. Employees currently and more than 2,000 contractors. Many of our offices are small, water resource related activities or other locales across the country, often in partnership with state authorities. And it's not just satellite observations; it's everything from stream gauges to seismic networks, aerial and satellite observations. The 30 petabyte remote sensing data archive at our Earth Resources Observation and Science Center in Sioux Falls, I think is the world's largest civil land remote sensing archive, and 3 orbiting Landsat satellites, with Landsat 7 actually just being retired, but still operated, and we'll get more information on that in just a moment. So our program of record, so to speak, for the Landsat program. See, covers the continued operations of the Landsat missions and the operation of the ground segment. Wide range of science and applications development relating to Landsat and the land data. So that's just one of many observing systems that USGS operates. We have a national stream gauge network. The seismic monitoring systems are global and international partnerships. Global volcano monitoring systems, and the not only Landsat but airborne LiDAR, National Hydrography Data Set, as well as. So by my own rough, and this is unofficial calculation, nearly 40% of the USGS budget supports multiple programs that manage these observing systems, operate them, and take care of their data. So moving on to next slide. So a word about our longstanding partnership with NASA. We're very appreciative of this partnership on Landsat, which is celebrating its 50th anniversary next month. July 23rd, 1972 was the launch of the first Landsat mission. And as part of this partnership, NASA develops and launches the spacecraft. USGS develops and operates the accompanying ground system, manages satellite operations, ground reception, data archiving, product generation, and data distribution. You can see the history of the Landsat mission operations here on the left, and in the context of what Waleed was saying about senior review board and how long satellites can last and data can be delivered. We run them as long and hard as we can until they're disabled or completely out of fuel. We've had some very good fortune over time with with our history in terms of the lifetime of Landsat 5 and Landsat 7. But we don't want to be complacent. In terms of the data itself, the animation on the right shows the growth of our global Landsat data archive since 1972. And each day we add in the land area equivalent of the continent of Asia into our archive. So this is a global survey mission. It's always on for all land surface, surface water, and coastal features. And the archive has really become a national treasure. For many years now, our program has really been driven by a rigorous user needs process, and I know Mike knows well about this from kind of a sister activity within NOAA. Given the relatively small amounts of money we're spending on space systems and data management, and wanting to be responsible. We've worked internally and with NOAA and other U.S. agencies to develop I would say, really kind of the gold standard for user needs analysis and architecting for best meeting those needs. So we do that through an elicitation process to both understand and then document user needs. We're one of more than 24 programs within USGS. We speak with each of those programs to understand their needs. We meet with other parts of the Interior Department, other U.S. federal agencies in terms of documenting what types of land remote sensing is needed. And then the division of our program that works on this seeks to identify the optimal architecture solutions to meet those needs, to take advantage not only of our own satellites, but other U.S. agency satellites and other foreign and commercial satellite capabilities, as well as other types of satellite, non-satellite information that can only be obtained through other means. So this feeds in quite nicely, I think, to the Sustainable Land Imaging Partnership we have with NASA, which I'll get to in a moment. But we use this process in partnership with other civil agencies, not only for our own mission, but also to share for NASA's mission formulation for the decadal survey or system observatory processes. Staff from our program participate in those meetings. This process also enables us to provide high resolution commercial data requirements for NGA and NRO, commercial data purchase planning and sharing with federal civil agencies. And we're reaping benefits from that now through the recently announced NRO contracts. And also enables us to work very closely with our international partners. And it's great to have Mark and Jörg on the line. We're working very closely with Europe on the Copernicus program and land imaging capabilities there. So I mentioned sustainable land imaging, and I was intrigued, I in terms of that, title and name. I think it does track back to kind of the decadal survey approach, and Waleed, you had mentioned kind of the category of sustained observables. For a long time, Landsat had been just kind of honestly kind of an ad hoc, new mission when it's needed. Not a lot of forward-looking investment in planning or very detailed governance structure. Lots of creative people doing wonderful things to maintain the data record, but understanding, we really need something more consistent and continued due to our users' needs and expectations and opportunities in the future. So the Sustainable Land Imaging Partnership is a joint activity between NASA and the Department of Interior and USGS, wherein we implement new Landsat missions. It actually bore its first fruits with the development and launch of Landsat 9, and we'll continue with Landsat 9's follow-on mission, Landsat Next. And this activity, the genesis of this activity actually goes back, nearly a decade when National Research Council recommended establishing a quote, sustained and enhanced land imaging program, unquote, to ensure continuity of Landsat data for the next 25 years. And what was stated as a comprehensive integrated program that capitalizes on NASA and USGS strengths, maintains current capabilities, and enhances imaging capabilities and data products via emerging technology. So the White House, NASA, and USGS certainly took notice and responded. If you look back to the Obama administration and National Plan for Civil Earth Observations and related assessment activities, this concept of sustainable land imaging was born and put into practice. And so Landsat 9 launch is the result of an earlier extensive architecture study and policy commitments and continuity by Interior, USGS, and NASA during both the Obama and then the Trump administrations. And so, observational continuity is foundational. Steady improvements were desired, and innovative technologies and cost efficiencies are sought wherever possible. And I think there was this realization and a recognition that land imagery, this type of moderate scale global survey imagery is as much a public good as GPS data and weather data to help us understand and manage our environment and address climate change challenges. So all this has been set up. We have the SLI governance approach listed here, and including agency responsibilities. And you can see it goes all the way up to our to the NASA Associate Administrator, Thomas Sarukin, and our own Assistant Secretary, Tanya Trujillo, for planning, leadership, and implementation. And technical levels, or managerial and technical levels, each level down, to ensure we're closely connected and kind of all rowing in the same direction. So this is Landsat 9 launch from Vandenberg Space Force Base in It's not as picturesque as Mike's lovely Florida image with the clear sunny skies. Very happy to have a good launch, even if the weather wasn't so great. So that's much more important. And there's just one set of facts you want to take away from Landsat about Landsat 9 today is it was a very successful launch, extremely accurate launch injection. All the planned commissioning activities have been successfully completed. Instrument deployments and activation are nominal. Successful underfly of Landsat 8 for cross calibration. Pretty much everything proceeding nominally, with excellent performance by the satellite and the ground systems themselves. So this is our current space segment for USGS. 2 operational Landsat missions, 8 and 9, and the recently retired Landsat 7, which has been moved into a lower storage orbit, awaiting one refueling mission. So this is an image of our EROS. See, over 10 million unique Landsat scenes available. Tremendous amount of data imagery available. 2008 processed collection 2. I think, as many of you are aware, in Washington, with kind of a rotating cast of congressional leaders, administrations, and so forth, it's always an educational challenge for us to kind of explain the uniqueness and the value of Landsat. This is our way of providing that. This particular slide, kind of shows its uniqueness relative to synoptic scale, and very high resolution, very localized scale of information. This unique and irreplaceable data record, the cross-calibration sensor data, and kind of the combination of scale, resolution, and global coverage over time. The observations from the shortwave and thermal infrared bands, which are not available in most other places, and really the breadth of applications that that it provides. So I think people often think of satellite observations and they think that high resolution means better, but that's only part of the equation. So the stability, the spectral quality, the accuracy, the science quality data over 5 decades is what makes Landsat continually important. So with regard to commercial satellites, there's been tremendous growth and tremendous opportunity with commercial Earth observations in recent years. Varying instrument sizes, capabilities, and data acquisition rates. A lot of this emphasis has been on commercial space data acquisition at high meters or less. Visible imagery with some near-infrared imagery as well. Constellations of CubeSats that provide near daily coverage. And these observations are tremendously useful and can be very valuable to federal civil agencies. But we also need to remind kind of our funding authorities and leadership that they really are complementary to Landsat class observations. They can't provide the long-term, well-calibrated, full-spectrum science quality data that Landsat missions traditionally have done, because of the size, weight, power, and cost considerations. So they also don't have the redundancy needed to guarantee coverage and science quality data. And so we think that these commercial systems can provide a tremendous augmentation and tremendous service to our many users, but they're not a replacement for Landsat types, Sentinel-2 types of systems missions. So moving into the future for sustainable land imaging, Waleed had mentioned Landsat Next, and Landsat Next is slated to replace Landsat 8, which is already 9 years old as of this year. So you can see that the has been S7, operating since 1999. Has just recently been moved to a slightly lower orbit, which is less busy and not a threat to other Earth observing missions, and awaiting the OSAAP mission. Landsat 8 still operating well, Landsat 9. Looking at the actually have, along with NASA, I think a very good future architecture concept, although the details are still to be finally worked out and announced with our budget colleagues. And say, and what's been shared many times previously, is the results of the user needs work that we've been doing for many years points to this level of interest and capability that NASA and USGS have been working toward in terms of possibly, depending on the ultimate architecture, temporal coverage. And from what we've learned from user needs, from the use of Sentinel-2 data by our stakeholders, our consultations with Europe as well. These improvements, moving to a super spectral type of capability will really help advance USGS science and other Earth system science in many ways. Going back to the history a little bit more, I did mention the transition to a full free and open Landsat data policy, which at its time we thought was really revolutionary and triggered an unprecedented wave of data downloads and use. Really helping to better inform productive and sustainable land and water resource management. The decision was taken in the George W. Bush administration in 2008. And you can see here that the growth just became exponential in terms of the amounts of data being downloaded by our users. And kind of the data architecture side of all this and the data reprocessing standardization side, I think is also a very ripe area for exploration by this committee because of what we found, kind of recurring new applications and value of data continuity. So along those lines, just over a year ago, we completed a massive job of the radiometry and geometry of the data, and it's called Collection 2, as opposed to which had resided at EROS and still resides there for a bit longer. And we did this through an Amazon Web Services contract, which enabled rapid processing of these data in weeks, versus what it took us to do on premises years to do when we created Collection 1 some years ago at EROS, which has its own tremendous supercomputing capabilities. And we've seen that since we've provided public access by the Amazon Cloud since last April, the amounts of data takes, people dropping in and kind of using what they need in the cloud has just exploded. We've had over 2 billion data takes since that time period. We thought 30 million Landsat images per year for the past several years was great, but you can see now that more total data has been accessed directly through the commercial cloud and the entire history of our program. So that's something that's very exciting to us, and the data architectures is something that I think we need to focus more on as U.S. agencies and with our international partnerships, because we think this really can revolutionize Earth system science. Our team is focused on long-term, more operational climate monitoring and forecasting capability, not just among our agencies, but among other. We like to point out, people outside of the science community often don't think of this, but terrestrial essential climate variables are in the climate impacts puzzle. And the data record of Landsat going back to the early 70s, coincides with the tremendous increase in temperatures and changes in Earth system dynamics. And so it feeds quite nicely into climate science. And see the quotes here, both from the research community as well as USGCRP in terms of the value of Landsat for Landsat class data for climate monitoring and application, climate monitoring and research. So this is kind of the cheese wheel or pie chart that we have. Uses of Landsat data from registered users out of EROS, from 2 prior internal White House-led Earth. Always ranks right at the top of the charts for utility across federal agencies in terms of different mentioned thermal infrared imaging capability earlier on, a very unique and important component of the Landsat. Here's just an example of some of the applications for thermal imaging. And there's just a few other applications just wanted to profile briefly in terms of vegetation and fire fuels mapping. That's contributed to many joint programs of the Interior Department and the Agriculture Department, US Forest Service, National Park Service. Better understanding fire dynamics, post-fire remediation, and climate change impacts. Monitoring trends in burn severity program, maps the severity, extent, and trends for decades of large wildfires across the United States. The land fire program provides this common all-source service of information for fire scientists at the federal, state, local, and other external levels. NSAD water monitoring and the tremendous droughts we're seeing out west, the continued growth in demand for insufficient water resources out west, long been a crucial application of Landsat data. Another interesting newer application has to do with the use of new channels on Landsat 8 and 9 to detect and address harmful algal blooms in surface and coastal waters, and better assess water quality in public health systems. I know most of our budget is focused on Landsat. It's really kind of a lot of other remotely sensed imagery, both satellite and aerial imagery that we bring in and distribute. Includes the land processes. Modus AHRR, really important data sources, Aster as well. And again, it's part of our mission to really bring whatever types of data sources are needed for our users beyond what we can build and operate ourselves. So partnerships are always tremendously important in leveraging each other's. This is just a quick shorthand list of our international sensing satellite activities, multilaterally in terms of operation of Landsat, bilaterally in terms of mission coordination, the multilateral work we do within GEO, CIRES, the Charter, and others. And we try to work closely with NASA and NOAA in all these activities, as well as kind of a whole host of support to national and international policy, White House, other federal agency, or international organized Earth observations activities. So, and I think these all kind of work in concert toward a greater whole. Our bilateral relationships can often complement how we approach things through multilateral coordination groups. And again, that's, among U.S. agencies here, and then with our key foreign partners internationally. And so it's really kind of a force multiplier, if you will, in terms of the capabilities. So Mark and I were joking earlier about being in different meetings at different times. We're always going to the same meetings, and one that we were just in, U.S. and European Union space collaboration. And within that, there's a Copernicus coordination group. And we've been using that activity against mutual objectives, both in Europe and the United States, for transatlantic land imaging capabilities, really to enhance the complementarity of our respective systems, complementary products, joint products, consultation, coordination, and mission planning, seeking ways to architect full, free, and open data for all of our users. This ultimately increased temporal coverage and increase other efficiencies and reduce costs. Much of it hinges on outstanding data validation, instrument calibration, quality control, and data standards. And we work very closely with our U.S. partners and European partners in that. And we see tremendous opportunity for doing it. If you look at the one animation here, you can see the Sen2-like product between Sentinel-2 and Landsat over a period of time. Getting a little more, I guess you could say, scientific in terms of the work that NASA and the European partners have been doing. Wonderful new harmonized Landsat Sentinel data product, which is going out the door pretty quickly from NASA Marshall. And so these are the kinds of opportunities and objectives that we see increasing our capability. Right now, where we are with Landsat Next and Sentinel-2 next generation, it's really kind of a once in a generation opportunity to maximize the return on our collective land imaging investments. Ultimately, the user doesn't care what the name of the satellite is, what country it comes from, if the data is useful and reliable and plays well with other data sets. It works very nicely. And we also see a lot of intercalibration opportunities in the future, which will enable us not only to just use Landsat and Sentinel-2, but for them to be kind of the benchmark and the gold standard for us to adjust and ingest all types of other government and commercial remote sensing data sources. So I have some backup slides with some pretty pictures of Landsat 9 imagery, as well as information on the organization, but and I'll look forward to questions to come.
Thank you, Tim. Our last presentation will be by a set of 4 speakers, and I'll introduce all of them, starting with Mark Dowell, who is the Senior Scientific Officer and Project Leader for Scientific and Technical Support to the Copernicus Program at the European Commission's Joint Research Center, where he also leads the European Commission's Knowledge Center on Earth Observation. Dr. Dowell's been heavily involved in the Committee on Earth Observation Satellites, CIOS, including serving as the first chair of the Working Group on Climate. He currently leads CIOS activities on the CIOS Carbon Strategy and Greenhouse Gas Monitoring Task Team and is the co-chair of the GEO Climate Change Working Group. Jörg Schulz is the Climate Service and Product Manager at the European Organization for the Exploitation of Meteorological Satellites, Eumetsat. He chaired the WCRP GWEX Data and Analysis Panel in 2014 to 2016 and the CIOS CGMS Working Group on Climate in 2017 through 2020. Jeff Privette is the Deputy Director of the Center for Weather and Climate at NOAA's National Centers for Environmental Information, where he manages their science and services portfolio. Dr. Privette also serves on the NOAA Advisory Board and on the Climate Working Group of NOAA's Science Advisory Board. And finally, Wenying Su is Senior Scientist at NASA Langley. Dr. Su has been a member of the CIRES Coordination Group for Meteorological Satellites Working Group on Climate, representing NASA since 2016. She also serves as NASA's point of contact to register the agency's climate data records in the CIRES Essential Climate Variable Inventory. Thank you so much to this set of speakers for working together to cover an almost impossibly large amount of information in a very short period of time. I really do appreciate their efforts to work together to do this. And with that, I will hand it off to Mark Dowell.
Thank you very much, Stacey. Good morning, I guess early afternoon to some of you. So I'll start this off. As I think you've understood, this is going to be a bit of a tag team effort. And what you can see, I guess, from this title slide, as many of the speakers have already underlined so far, is really this is a lot about partnerships. Because I think what we've found in working both at the European level and in some of these international programs that we're going to address is really that if we want to kind of ensure the long-time continuity of some of these satellite data records, some of these partnerships are actually quite effective mechanisms for getting at that. So I'm going to start, if I can have the next slide, Jörg, please. So I think this is just a quick overview of the different topics we're going to address. I'm going to start off with a bit of an overview of some of the kind of the origin story of some of the international coordinating mechanisms, and then start to tell you how we address some of that in Europe. I'll also give a brief introduction to some of the Copernicus, kind of the more programmatic setup of Copernicus as a program. And Jörg will go into some of the more details on the activities, both within Eumetsat as well as some of the other kind of activities in Europe and how we've benefited, let's say, from some of the international interactions that we have. And then Jeff and Wenying will come in at the end and show how we've kind of built on that now to really kind of coordinate the data records and observations. I thought one of the comments made by Waleed in the first talk on the focus on observables is very relevant to, I think, some of the approaches that we've been taking as well in some of these international discussions. And you'll see that in the last section by Jeff and Wenying. Next slide, please, Jörg. Yeah, if you can go forward. So I think, and what I realized was that when I was listening to the previous presentations is our focus is quite specifically on climate observations, although I think a lot of the kind of the approaches and best practices that we've used and adopted are applicable to some sustained observations for other application areas as well. So just maybe bear that in mind as we're going through some of this. And kind of the starting point for a lot of the discussions and the kind of the developments as far as kind of the international coordination mechanisms is the fact that within the United Nations Framework Convention on Climate Change, what they call in their terminology, what they call systematic observations is actually a fundamental part of the original convention. Recognizes its input both to advancing the state of science on climate, but also providing actionable information to the parties or the countries that are members to this convention in kind of thinking of how they address climate issues, whether it be through mitigation or adaptation measures. Next slide, please, Jörg. And the setup kind of in the UN context has really kind of been underpinned by these three fairly high-level conferences. That the first one in 1990, then in 2000, then in 2010. And from a key perspective, what these three conferences have done is they've resulted in fairly substantive programs addressing different areas of this. The first in 1990 established the World Climate Research Program, which I'm sure as many of you are aware is providing a lot of the underpinning science that is used, for example, in the IPCC assessments and elsewhere, and really has been kind of the scientific forum at the global scale for discussions on climate issues. The second conference in 2000 established the Global Climate Observing System, and we'll be focusing quite a bit on that in the context of our discussions today. And GCOS provides the basis for climate observations, or the systematic observations in support of the convention, which kind of then provide us with the basis of a means of addressing the specific needs of and requirements that are identified by GCOS. And the third, I think, is also important because it provides an avenue for and an opening for additional needs and requirements that come basically from the broader world of climate services through the establishment of the Global Framework for Climate Services. And this means then that we have another layer of requirements and needs that are coming into this that are not only kind of dictated by the needs of climate science, but really in providing actionable services that can be used by a wide variety of stakeholders. Next slide, Jörg. So coming to GCOS more specifically, I think there are a couple of characteristics of GCOS that make it very useful as a program, and that at least in Europe, kind of we decided to almost adopt as a template, as I'll show you in implementing our programs. Firstly is the fact that it has this kind of iterative cycle that goes through a process of characterizing requirements for climate observations and products, and in identifying actions that need to be undertaken, and then after a certain period of time, assessing the status with respect to those actions and of the climate observing system globally as a whole, identifying gaps, or for example, gaps in continuity of certain data and products, and then providing in the next cycle additional actions to identify and fulfill those gaps and fill those gaps. And of course, because this is then reported directly back to the convention, the countries and parties to the convention through the negotiations, for example, at the COPs, are expected to address those actions and do so, for example, through frameworks such as the World Meteorological Organization and others. So that's the first element, is this kind of repetitive cycle, which has kind of basically a 5-year iteration between one implementation plan and the next. The second is kind of the characterization of these essential climate variables, which basically cover all of the domains, and are providing and refining gradually over time the requirements for the specific data and products that is required for the subsequent users. Next slide, please. So I think the next slide just basically will show you this repetitive cycle. I'm not expecting you to read this, but you can see here the different GCOS implementation plans, the actual IPCC assessment reports, the GCOS status reports, and how there's this kind of ongoing cyclical improvement of the process as it goes forward. Next slide, please, Jörg. So in Europe, coming a bit of history, how we kind of use this to address these issues. More than 10 years ago, actually back in 2008, the Space Council of Europe, which is basically the European Union Council, so all of the European Union member states, the ministerial representatives for each of the countries of the EU that have some responsibility for space made a request to the European Commission to make an assessment of Europe's capacity for looking at space-based observations and what will be needed to kind of advance that in time. And so, with some colleagues at the Joint Research Centre, the European Environment Agency, European Space Agency, and Eumetsat, as well as ECMWF, we made an initial analysis of what the potential was for addressing climate observations and what Europe what assets Europe already had at that point in time and what we needed to do to kind of come up with a more structured approach to how we were addressing this. And what we found out fairly early on, that to use kind of the GCOS template of the essential climate variables and the actions that were in the implementation plan, as well as other guidelines provided by GCOS, was a way that both we could kind of measure the current state of Europe's capacity, but also starting to think about what the respective responsibilities could be of the individual agencies in making sure we address this in a more structured way. So think of the responsibilities, for example, of the European Space Agency in both developing and launching satellites and advancing the state of the art in that observational capability, the responsibilities of Eumetsat in providing sustained delivery of products through operational ground segment and operating satellites in particular in the atmospheric and ocean domains, and the responsibilities of ECMWF in providing the kind of the backbones of reanalysis, climate prediction and data simulation, so that we could develop climate services or core climate services at the European scale. And so this initial analysis then went into the thinking. This was about the same time, by the time we'd finished this process, which was around 2010, 2011, it was when we were starting to think about the first operational part of the Copernicus program, which started in 2014. So we were able at that point then to build on the existing kind of prototype services that we had for land, ocean, atmosphere, and provide an additional service dedicated on climate change and underpinned by all of the data processing and data records that were required. Next slide, please. And what we saw was, okay, as far as the space-based capabilities, there were about 31 at this point in time, of course, 31 of the GCOS ECVs that could be measurable from space. And Europe had a capacity at that point in time to address 29 of these. But only about 40% of those were currently produced systematically through the various programs that were starting up at that point. This is when Copernicus was still called GMES, and the ESA were just starting the Climate Change Initiative program, and Eumetsat had its climate SAF and had just actually, I think you can correct me, but if I'm not mistaken, at just point in time, it was formally recognized in Eumetsat's legal constitution that they had a responsibility for climate observations and data. So all of these things kind of coalesced at the same time. They provided us an assessment of what we needed to do to advance the state of the art, including, for example, on reanalysis. I was telling an interesting story to Jörg, Jeff, and Wenying when we were in a preparatory call for today, that I remember being in the room when we were talking about reanalysis, and the colleagues from ECMWF were explaining all of the uses of their current reanalysis. But at that point in time, the reanalysis was really just carried forward from one research project to another, mainly based on the framework program funding in the EU. And there were some colleagues in the room also from some of the funding ministries or DGs of the Commission, and they said, well, you know, how much are we talking about to do this reanalysis in a more sustained way? And it turned out to be something like about €8 million a year or something like this. And so, you know, the reaction from these colleagues who had the opportunities to fund these said, well, okay, this is something we should do and we sustain it in the long term. So it basically went from that simple conversation into becoming a line item and is now an operational part of the service. Next slide, please, Jörg. So, okay, I'm going to make the link now between the European and international aspect. Of course, we were having those discussions. As I said, we based this on kind of GCOS almost as a template for us to both organize ourselves and think about what we needed to do. We recognized straight away, of course, that some of this needed to be done through international partnerships. And so we started discussions within CIOS, the Committee for Earth Observation Satellites, that there needed to be some coordination mechanism so that these efforts could be brought together at the global scale as well. And that then was the creation of this working group on climate in CIOS. And soon after that, the coordination group for meteorological satellites joined this. And we also got together at that point with WMO to think in a more structured way about what a global architecture should look like for climate observations as far as producing these data records in a systematic way. And I think it then occurred to many other of the agencies that this was also an opportunity for them to structure themselves internally how various agencies at a national scale could make contributions. As I said, we started then to get additional requirements from these climate service activities, and then that, of course, feeds back into the GCOS process. It's not only, of course, coming from GCOS, there are additional user communities and requirements in other international coordination mechanisms, such as in the group on Earth observation. And many of the products you heard Tim talk about in the previous thing, whether it be global scale forest distribution or global scale products for agriculture monitoring, they're largely catered for within these activities in GEO as well. So I think, is that my last slide now, Jörg? Am I passing back to you?
No,
oh, no, sorry. One more. So this, yeah, is just to say that architecture diagram I showed you in the previous slide, that is resulted in this strategy towards a climate architecture from space. And then that kind of, which follows a fairly strict value chain analysis. I know Jörg will come back to this after. And just think about this as well. I think Waleed was making in his earlier comment, this focus on observables. And that puts you kind of at a place in the value chain where you're looking both ways. You're looking both towards what the implications of those observables are from in kind of sustaining the space segment contributions, but you're also looking downstream to what the potential applications and what the users are asking for, so that kind of dictates and helps you prioritize almost the climate observations that you really want to sustain into the future. So I'll pass to Jörg now, who will deal with, I'm going to say a couple of things on, I'm passing to you, Jörg. Yeah.
Yes, yeah, thank you, Mark. So I will continue that a little bit with talking about the European program development of the climate observation capability. So you will see some figures that you already know now. So one is, this is basically showing you a little bit the climate monitoring architecture at work. It has a Eumetsat bias because it's from a slide that I developed for Eumetsat, but largely it applies also to ESA and also to Copernicus that you see on the left. So this is the same value chain that we have seen. And if you look on the right, so there are parts like decision making, which is of course the policy needs of UNFCCC, but also a lot of sectorial application and policy areas that needs a lot of decision making. And those listed here, I think they are just those from the European Union, and there might be more on the national scale. And in terms of applications, if you go one column to the left is, so one thing to serve, of course, with all the data is the scientific needs, which is represented here by WCAP and the ISA and JAMC and also the IPCC assessments that have also where some measurement needs originate from. But then, as Mark said, there is a whole set of climate services, and they exist at the European level with the Copernicus Climate Change Service, but also at the national level, because many of the European countries develop their own climate services, and they have very dedicated national needs, which we also try to serve. So these two columns basically provide all the needs for what we actually need to measure, deliver, and tailor down to the needs of the so to speak customer. So on the left two columns, you see what we can actually do. So the sensing column, so that's basically about the hardware in space, but that means things like long-term satellite programs, and we had already a discussion earlier about continuity. Of course, you need patrimonial archives, and these archives need to be maintained to the lowest level of the data. So the first thing to secure is that you never lose any level 0 data from these platforms, including all metadata and associated information with them. But it also means things like data rescue activities, and I'm grateful to NASA that they actually do some of those, so that you go back in time as far as possible. And I think Tim has just shown with the Landsat series how valuable that is in 1972, but there are even data earlier than 1972 that you can actually utilize. And then, of course, with each new mission, you get also a better instruments, and that allows you to expand the product portfolio until better coverage of the GCOS ECVs, but also covering other variables which are not GCOS ECVs. And then, of course, an important element that also needs funding is how to produce climate data records. And basically in Europe, it is Eumetsat with the SAF and ESA and Copernicus. We are all engaged in doing that with various means. So this is doing data records from satellite data directly, combining with in situ data, but also through global and regional reanalyses by assimilating the satellite data into basically numerical weather prediction models at different scales. Important is, and this is a task that sits mostly with the space agencies, is consistent calibration and recalibration and cross-calibration. So this means a really dedicated analysis of each sensor record and try to improve, to optimize the calibration, even for past measurement or for each individual record from whatever you know. Derivation of geophysical parameters, a dedicated uncertainty analysis, and more recently we actually started using methods from metrology to do that. And then, of course, things like data access, and Tim also brought an excellent example on how you can use cloud infrastructure to get this really boosted out to the community. But also cooperation with users and training is important to address the right pillars, because in National Climate Services, the people are not really familiar with satellite data. So you need to do a transfer into this. Okay, so as usual for a space agency talk, of course, we also need to mention the space segment capability. And this is a slide that's constructed by ESA, but it shows very nice how the European space segment lines up. So you see here in green, so these are all the scientific Explorer missions from ESA, and I have no time to talk about each of them individually and what parameters they do, but I just want to highlight one here in the middle. I don't know, can you see my cursor? Maybe this is the Schulz mission, so which is a kind of a complementary thing to your Clario mission of NASA, so providing a traceable reference in space for the visible spectral range, and this will become a true intercalibrator for many other visible spectrum measurements. And then you see these are basically the kind of research missions. And then you see in blue, this is the Copernicus, so the European Commission-led space segment with all the sentinels. And important for the continuity of record is, of course, if you look here for things like your Sentinel-3, you can even, it's hard to find the start. Here's the start. Sentinel-3A is in space, 3B is in space, but then there's already a 3C, a 3D, and then there will be a Sentinel-3 continuation mission with some more features. And the same applies also to Sentinel-1, 2, and 6. And if you then move over to the Eumetsat operational missions, which are more on meteorology and ocean, but you see also here that we have for Sentinel-4 on a geostationary satellite, Sentinel-5 on our future polar orbiter METOP second generation. You can see there's a lot of interaction, and an implementation of this is, of course, that each of those have different funding streams by the member states of the organizations. But then, of course, ESA is mostly in charge in developing instruments and bringing stuff into space, and operations is more and more shared between ESA and Eumetsat for many of these missions. And there will be more details in the next few slides. So with that, I go back to Mark. I think this is a little bit more about Copernicus, and I think you have 3 slides to talk to.
Yeah, thanks, Jörg. And I'll go very quickly over these because I'm conscious that we're already using quite a bit of time. So I guess with this first slide, I just wanted to underline, and I'm sure many of you are familiar with this, first of all, that Copernicus is not just about the satellites. It's really about, it's a user-driven program. And I think its intention is to be operational, which is what it is. But it covers a very broad range of services. So it's not just focused on maybe some of the traditional fields we think of for operational products and services, such as in meteorology or ocean products, but it really covers a very broad range of areas. And the kind of the enabling mechanism for this are the core services. So we have core services for land, atmosphere, and ocean, climate change, as I mentioned before, security and emergency management. And then, of course, there are in situ program. There's an in situ component. The Copernicus program itself doesn't actually pay, or not to a large scale, for the in situ observations. It's expected that the European member states are covering that, but it does provide kind of coordination mechanisms and data access activities on this. So if we can go to the next slide, Jörg. The other thing I wanted to point out on the governance is about the governance. And yes, it's complex, but someone said to me once, it's like a train that takes, you know, a long time to get off with too many carriages, but once it gets going, it's never going to stop, because no one wants to be the person to break one of the links of this system. So we have, of course, the European Commission is the program manager, and our responsibility is to ensure that the program is implemented adequately, that we need to provide the requirements for the implementation and evolution of the program, and we need to evaluate and assess that it's been implemented adequately. Then, of course, the European Space Agency and Eumetsat are contributing both to the space segment and ground segment activities, and then a broad range of European agencies. I'm sure many of you are familiar with ECMWF, but there are a number of others that provide the services. And then, of course, as I said before, the in situ is from the EU member states and coordinated by the European Environment Agency. Next slide, please, Jörg. And then finally, Jörg already alluded to this, but we also have the ambition that the program is not static. So within the budget availability, our ambition is to evolve the program. What we're looking at the moment are the so-called expansion missions. So this is following on from the original Sentinel constellation, and there are 6 missions being considered. At the moment, all of them are being developed, but we still have to look at budget availability to actually take these to completion. I think the CO2M mission, which is kind of one of the flagships of this new contribution to the constellation, looking at anthropogenic CO2 and actually methane monitoring as well. There are already 2 of the 3 satellites in that planned constellation which are available, which are funded, sorry. But as you can see, a broad range of other areas to complement the existing constellation. So back to you, Jörg.
Yes, so I dove a little bit into the Eumetsat context for climate engagement, and so Eumetsat is run by about 30 member states, and of course they are represented in what our council is. And actually the update of the Eumetsat Convention to do something about climate change was actually in 2000, not in 2008, but in these first 8 years nothing really happened because there was no budget. And there was not a clear pathway of what the organization should actually do or what the SAF network should do. But we have this since then as a further objective, as you can see on the left. By now, this has found its way in our strategy that was just updated last time, and it's even more detailed into a strategic framework for support to climate services, so how we do things. And then you see on the right what it results in is, of course, it is on the production of data at the Eumetsat Secretariat. So we have a specific plan for supporting climate services, which is a lot of data records. We have a similar plan which is called a Copernicus reprocessing plan, which cares for the reprocessing of all the Copernicus missions that we operate. And then we involve our SAF network, and they get into 5-year slices and support all these activities. But there's also impact on the infrastructure. It also issues basically requirements to the operational missions that we plan, and some climate requirements like orbit stability or so are pretty important to get to a high stability of the resulting record. And then very much below there's also a symbol for it has also a lot of impact on the compute infrastructure. Okay, so this is the context, and I just show you our long-term mission plan. So you see at the top the Eumetsat first generation. I think that lasted with 7 satellites for about 40 years. So that's quite a good record. And then you see the second and third generation are emerging, and we hope to launch the MTG I1 actually in the last week of November this year. And this will be a new era because that is the first GEO constellation that we're going to fly. But the important thing here is that, so you have three programs, first, second, third generation, and we always care for a lot of overlap between the satellites in space. So it's important for weather prediction and nowcasting on the GEO, but it's also very beneficial so that you have a hot backup in space, but it's also very beneficial for understanding the measurements if you have overlapping missions. And we try actually to do the same with our polar program on the METOPS. So we deorbited METOP A in November, but then we had at that time all three satellites in space at the same time, so we can really compare this measurement by indirect means. And then there will also be a second generation. And then, as we have seen, we operate a couple of other missions on behalf of the European Commission, or for that it was an optional program. It's now also Copernicus on the altimetry, and we will of course continue that. So to demonstrate that there's also one element on research to operations in the hardware. So most of you know that ESA has flown the IOLOS mission for wind in the atmosphere. And of course, we already now think about an operational Doppler wind lidar program. And this is a kind of in the first stages of making a program proposal to get this into orbit by 2030. Similar things happen also with mini satellites in constellations of microwave soundings, where there will also be first an ESA Earthwatch Arctic weather satellites, but then it should emerge into an operational constellation, and the time here is pretty ambitious to do this in 29. We have seen that in the past, from the EAS scatterometer to the ASCAD, from the GOMI to the GOMI-2 at Eumetsat, and now to the UVNS within the Copernicus Sentinel 4 and 5. So this is a long thread of research satellite to operational satellite transitions. And then there's also a commercial element eventually on radio occultation constellations. So there are a lot of data buys going on. I think NOAA is doing similar things. On these, for climate, one needs to be very careful in evaluating the value of this and how much impact you can actually have on what you will get in the future. But it is considered because having constellations and RO is basically a good thing that we can easily compare with each other, the individual instruments, because they don't need any cross calibration. So that's to show you how research operations works also on the space segment. Then the SAFs, we have that. So there are 8 SAFs, and they basically all contribute to climate, although they have names like climate, radio occultation, ozone, but they all produce climate data records. And they just had the 25th anniversary. And so the governance is done by our member states, and we basically invest into the SAF network on a scale of 5 years, about close to 60 million euros to finance that. And it's executed, as you can see in the map, by our member state organizations themselves. We produce a lot of ECV data records, and you see that a lot of those coming from the SAF network, and also at the Secretariat we do a couple of them. It's just a nice colorful example. This is not all we have, but there's much more. But just show you on the lower left, this one is based on the full record of the AVHR going back to CIRES N, where we of course also work on recalibrating AVHR instruments and to get to a consistent radiant series before we embark on deriving things like upper air wind vectors, what you can see in the plot here. Okay, ESA is doing similar things than Eumetsat, so this is not such a big separation in the objectives. It's more a matter of the coordination and complementarity of our activities. So ESA has the climate change initiative, as Mark mentioned, and they respond basically as we do to the GCOS requirements of UNFCCC and follow the same aims and objectives, but doing this for other parameters. And you see here the impressive set that the ESA CCI has put up, and the ESA member states are actually providing good funding for those. And I hope they will continue also in the future, because having these two programs actually together with the Copernicus makes us even stronger together in doing these things. And one thing on the C3S, so at Eumetsat, we are actually really supporting the global reanalyses, and you can see why. So this is showing you on the left the satellite product, CIRES-X10, which is starting to derive from microwave imaging. And then you see, if you want to put some context, you would need also a lot of thermodynamic and dynamic information, which is probably better to be provided by a numerical weather prediction model. And as Mark said, the 8 million for the reanalysis, now it's a little more of investment, and actually we benefit from that as well. So by that, we are now a major provider of all these data that see on the right that go into the reanalyses. And there we do not only work on our own data, but also on the rescue data for the past. And we also work on a couple of the American data sets like HERS, MSU, so the whole microwave sounding fleet. And this is very valuable. And then we help them in the assimilation into the global model. So there's a big collaboration that goes on with ECMWF in the context of the C3S. And with that, back to Mark.
Yes, so just a few slides on the C3S itself. I think many of you may have be familiar with it, but when we set it up, we realized, okay, we needed to both have the climate, basically an entry point, the climate data store, which, as I'll show you after, includes all of the observations, the reanalyses, as well as the model output, both for seasonal forecasts and climate projections. There are sectoral information systems, which then transform that store into specific applications for different sectors that are interested in developing climate services. And this is more to basically, I would say, stimulate a more general interest in using these products in different applications. So it's not that the ambition is to sustain these all through the C3S in the long run, but more to demonstrate the capability of using this data for climate services. There is a component which is looking at evaluation and quality control, which is across the whole service, as well as an element on outreach and dissemination. Next slide, please. And this just gives you a list of the type of products, as I said, across observations, climate reanalyses, and model output, where the model output is addressing both seasonal forecasts and climate projections. As we've kind of tried to stress, I think now on a number of occasions, this idea of using the essential climate variables for many of the observations almost as like a standard template, we found to be very effective in the context of the C3S, and actually the European Union member states kind of put that as their top priority before we started this service, in that they wanted to see systematic production of these products. Of course, it relies again on this kind of iterative process of the GCOS actions in the implementation plan and the requirements, as well as the status reporting, but also provides support, of course, to the IPCC assessments and CMIP. So basically, they started this in 2014, and I think by 2017, they were basically fully operational. So I think that's really a tremendous credit as well to the colleagues at ECMWF that they managed to put everything together in less than 3 years. Next slide, please, Jörg. That's yours.
Oh yeah, I can take that. So this is just so, as we have seen, so the climate data store and the toolbox. So that's a very cool tool where you can actually bring also all data to the same standards and make them much better accessible. And we have started in Europe, of course, to do transitions. So from the ESA CCI outputs, from the research to operations, and you see this massive set of GCOS ECV. So each of them represents one CCI project, past or ongoing, and they basically all gonna be transferred or are transferred already into this climate data store. So from Eumetsat side, we do similar things with a SAF network from operations to operations, so to say, because we produce them operationally. ESA is more on the research, and there are less variables, but this list will also increase. And then we all meet basically in the climate data store, where you get them basically all in the kind of same format. And this is really multiplying access for everybody's data, because everybody by now knows this climate data store. So it gets really a very central function, and the collaboration among all these entities works amazingly well, I must say. So next slide is yours, CO2.
Yeah, so the last few slides, just before we pass to Jeff and Wenying, is basically to say, you know, there have been points in the Copernicus program up to now where we've basically identified a fundamental gap that we felt we weren't addressed. And this was the case around 2015, around the time of the Paris Agreement was being negotiated, where just before the Paris Agreement, we realized that Europe really didn't have within the current capabilities of the constellation of Sentinels and the Copernicus program itself, the capability to monitor greenhouse gases. About a series of studies to kind of understand what type of requirements would we need to address to be able to identify both detect and monitor point source emissions, and also assess longer term changes in emissions at the level of the so-called national determined contributions, which are a fundamental part of the Paris Agreement and the global stocktake, so that on the long time we can really assess the changes in national emissions with respect to that stocktake cycle. Of course, these are quite divergent requirements, and so they're really kind of imposing on the type of satellite contributions and the actual data simulation system that would need to be put in place. And in fact, as I said, the CO2M is actually a constellation, an all-in-orbit constellation at the same time. We initially are targeting 3 versions of CO2M in the same constellation. Although, as I said, at the moment we have money for 2, and we're trying to find the additional budget to be able to launch the 3rd, so that we have 3 satellites in the constellation at the same time. Next slide, please. And I should mention, I see a question in the chat from Dwayne. Yes, all of the expansion missions will then continue in the life cycle in the existing Sentinel constellation, so they'll be kind of repeating versions of these sensors going out to the future, and actually it'll come together in what we call the Sentinel Next Generation, which will start in the 2030s, and which should bring together and continue and provide continuity to both the original Sentinel constellations, probably with some modifications, and we heard that there are ongoing discussions, for example, with USGS and NASA on the Sentinel-2 Landsat kind of synergies and where we see that going in the future. But the same is true for many of the other sensors. There will be changes based on evolving requirements, but the expansion missions will become a part of that longer term vision. And so, okay, this, I don't know that I need to go. This is just showing some of the rationale for this CO2M initiative. Maybe just the last slide, Jörg. I think another important part on this, and this is why Copernicus as a program, which is integrating the satellite observations with the service components, is critical, especially for addressing applications like we're foreseeing for the CO2 and greenhouse gas initiative, is that really we see this as a system approach, bringing together the observations with in situ observations as well, an integrated data simulation system, as well as bringing in case of greenhouse gas monitoring, of course, we need to bring in the activity data as prior information into that data simulation system as well, so that we can address all of the range of outputs I showed that are dictated by the requirements a few slides ago. So I think now we're passing over to Jeff and Wenying.
Great, thank you. Can you hear me?
Yes.
Okay, thanks. I've had a little bit of audio problems, but I just wanted to check that first. Thanks very much, Mark and Jörg. Excellent presentation so far. I'll try to keep that going. So now I'm going to talk about what we do in climate observations and data records. And particularly, I'm going to be talking about the joint CIOS-CGMS working group on climate. CIOS generally has a little bit more background. It's a larger organization involved mostly with research space agencies around the world, but not exclusively, involved in coordinating missions. CGMS is largely more concerned with sustained meteorological type observations, but not exclusively. And you have multiple agencies like NOAA, which are involved in both sides of that. So we are a group that reports to both of these. And this first slide just sort of shows our relationship. We're on the far left, involved in observations, as Mark sort of walked through before. We do respond exclusively to the requirements of GCOS. And we work very closely with WMO in doing so. We support the other functions on the right, the research, the assessments, and the policy. And we work closely with all of these different groups. It's probably important to note here, what you don't see are things like commerce and industry. And while a lot of what we do supports commerce and industry in the various nations, those are not our drivers, and that's not what we're responsive to. Next slide, please. And this sort of just, you know, it shows a lot. There's too much to go over here, but it just shows that we are working with WMO and other organizations to understand not only what, well, three different things. One is sort of the historical record of satellites that have been up and are no longer functioning, those that are currently in the space architecture, and the future space architecture. So we're looking at the past, present, and future as we're trying to understand and potentially find gaps or things that need addressed in developing the climate data records. Climate data records effectively are our currency. We're not looking at sort of one-off demonstration missions, but much more involved in the sustainment of observations, which have been proven useful to climate measurement and monitoring. So the left shows sort of the constellation. The right shows the kinds of things that we're interested in. So for instance, this is for geostationary satellites, the so-called mosaic or quilt. And you see on the y-axis, that's the years, and on the x-axis is the longitudinal coverage. And it is indeed a patchwork, and it's tricky to keep track of, but an organization, and it happens to be our organization, is trying to make sure that we keep that completely covered so that we do have the so-called geo ring in place and provide that continuous coverage around the world at geostationary. Next slide, please. And this just shows, again, a little bit of our relationship to GCOS. We do take our requirements from GCOS, we react to them, we take a look at the climate data records through our inventory, and we assess where there are needs or gaps. We provide a response back to GCOS to explain how well their requirements are being covered and how where we see concerns for the future. We, as a group of space agencies, we can initiate the talks and discussions to be able to address those gaps in the requirements. And we do provide an annual report up to the COP, at the annual COP to the United Nations and UNFCCC. And that's sort of an important overall role. We are the single conduit for official communication up to UNFCCC for the space agencies around the world. So that was sort of a quick run through maybe the roles and the context that we have in the working group on climate. I'm going to pass now to Wenying, who's going to talk a little bit more about how we operate, the mechanics of how we operate, and the capabilities that we have.
Can you hear me?
Yes, we can.
Great, thank you. So yeah, so many speakers have demonstrated the international space observing segments, and from those segments that the climate data records are generated. So one of the main tasks for the joint working group on climate is to take the current and future landscape of how the climate data records are covering the GCOS essential climate variables. So this is done through the ECV inventory. So basically, this inventory is describes the current and future planned climate data records. So I want to clarify the plan, meaning doesn't mean it just only have to be coming from the future missions. It can also coming from the legacy missions that can be utilized to generate climate data records. So we currently having the latest version is the version 4 ECV inventory within this version. So all the CDR contents in there are fully verified, and most of the data in there are actually freely accessible to the users. So it provides a lot of information of the CDR generation, what satellites used, what the quality assurance are used, and the the accuracy, stability of all that, and then the application potentials of those data sets. So using this the ECV inventory. So another activity that we routinely carry out is the gap analysis. Basically, that exercise will address the completeness of the ECV products and also the sustainability of space segment. Also, we address the missed opportunity for CDR generation from existing observations. So with this, we come with the recommendation and also action plans to space agencies to mitigate any potential gaps in the ECV inventory. Next slide, please. So this is the web page of the ECV inventory that is managed by Working Group on Climate. So you can see that currently we have over 1,100 CDRs in the inventory, covering almost all ECVs that identified by the GCOS, except the ocean surface currents and the anthropogenic greenhouse gas fluxes. So a bulk of about 70% of the CDRs actually in the atmosphere domain. I want to highlight the bar charts at the bottom here, so you can see that just for each space agency, the relative contribution to existing and planned CDRs between 2018 and 2020. So you can see that even in 2018, there's a lot of agencies has plans to producing climate data records, but just within very 2 years, most of their commitment to generating climate data records actually materialized. You can see that 2 examples are USGS and European Commission. Back in 2018, most of their or all of their CDRs are in the planning phase, but by 2020, that's almost all actually the produced CDRs. So given that, we'll come to the next summary slides. And I will just leave on this since we're running really short on time. So folks are interested can just take a look while we get into the discussion sections. Thank you very much.
Thank you all so much for the presentation. And as I invite participants to raise their hand if they have questions, I'll go ahead and get started with the first question. In what parts of the Copernicus framework do you see opportunities potentially for coordination or participation by U.S. agencies? You described sensors, products, records, in situ. Surely some of those are easier than others for coordinated international efforts. Is there a process in place, or is there an opportunity there? I'd say either Mark or Jörg.
Yeah, I mean, actually, as Tim mentioned, the one of the venues, at least for that opportunity, was happening yesterday and today in Washington. So there's 2 structures. One that is called the Civil Space Dialogue, where there are basically meetings between the at a fairly high level between US and EU, both the Commission, actually it's the US Department of State that leads on the US side, but then all of the agencies on the US side are involved, and the same is true on the European side. And that is where they talk about kind of fairly high level things as far as coordinating space segment aspects, mainly focused perhaps on space segment aspects and products. And then there's another mechanism which is more specifically on Copernicus, called the Copernicus Coordination Group. And there, as Tim said, there are specific activities that are ongoing, for example, on land surface imaging, and others that are planned. We actually discussed a specific idea to go forward with a similar model for the greenhouse gas monitoring activities. So that, I would say, is pretty much on the space segment coordination. Of course, there are very clear examples such as Sentinel-6, where there's already a partnership between the EUS actually on that satellite. I should mention that individual services, so C3S has bilateral collaboration with various agencies, in particular with NOAA, a fairly substantial collaboration in the implementation of the climate change service, but it's true as well for many of the other services, for the marine service and for the land service. There's collaboration on that on those more product generation and service delivery elements. So yes, absolutely. I mean, there's a number of mechanisms that exist, and of course there are more kind of dedicated discussions as well between ESA and on many of their other programs, and Eumetsat, not only within Copernicus but also on their institutional programs. I don't know, maybe Jörg wants to add something to that.
I think I might add that actually also good and old collaboration mechanisms like the CGMS help, because the climate monitoring, of course, also benefits very much for what is happening on weather prediction. So the whole fleet of the meteorological satellite, and we saw that in the NOAA presentation, so that there are these agreements between Eumetsat and NOAA that we share orbits. So we do mid-morning, NOAA does afternoon, and somebody, maybe China, needs to do early morning. And this, of course, also helps sampling with comparable measurements in over time. But what is probably needs improvement is that, of course, the instrument designs are different. So we were benefiting from NOAA instruments being flown on MEDOP. So like the AVHR remaining flight models and HERS and AMSU-A actually. But now we don't do that anymore. So we had even a bigger integration for a time. Now we develop all our own instruments. And I think what we need really to be careful with is, we have all this innovation, of course, in the technology, but we need to carry on the same kind of frequency measurements. So this is like for the GEO, since the beginning of our Megasat first generation, we always carried 6.7 micrometer water vapor channel. And this is in the second generation, it's also in the third generation. And then you can add other channels to complement that. And I think in the past, there was in this architecture document that Mark showed a good example of HERS, where it actually went wrong for one of the water vapor channels, and you have destroyed the continuity of record. Altimeter is also a good example of Sentinel-6. I think following altimeters need to still carry a low resolution mode measurements, otherwise you would also destroy the continuity of record. So in that sense, and this needs to be coordinated, in particular in those missions where we share a lot of responsibilities, which is complex but also quite enjoyable to do. And I think CGMS is a kind of operational, is almost often the right place to do this for the more mature missions. And then in CIRES, one can also discuss a lot of the new missions that come up, and also maybe how to transfer them into operations. I showed a couple of examples on the institutional level, but this could also be done internationally more.
Great, thank you. I see a question from Graham Stevens.
Yeah, hi, this is a question. First of all, I want to say, Jörg and Mark, that was a great presentation. And this is a question that has to do with a little bit of, I guess, with GCOS. And it may reflect my lack of being unconnected to GCOS for many years, but and it stems from the fact that I believe that we have a number of gaps that exist with respect to monitoring Earth's climate system. And you talked about gap analysis with GCOS. And also, I also believe because there are gaps and because, these measurements really are quite costly, we have to start to think about how do we set priorities. So this comes from the point of view of how do we identify priorities? And so what I think we can learn a lot from what GCOS, how it's evolved in the last 10 years. And I want to kind of get an idea of how is GCOS doing gap analysis? How is it identifying what's important gaps that exist? And how is it setting priorities? So for example, essential climate variables, the word essential, I think implies that you've identified a priority, that these climate variables have a priority. I just want to understand, how did you come to setting these priorities? How did you determine these were essential? Because I think we're going to be faced with this more and more down the road as we try to figure out what we have, how to prioritize, what we need to do versus what we can afford to do. So really, it goes back to questions about GCOS and how you're setting these priorities within GCOS. What's the mechanism and how can we learn from that?
Yeah, I mean, I can start, Jörg, if you want, and then maybe you can. Yeah, I mean, okay, firstly, maybe a caveat. Of course, we are not really GCOS. Yeah, we're kind of responding to GCOS in a sense. But we have been involved, definitely, as Jörg said, and Jeff pointed out. Actually, there is kind of this iterative feedback. But I think it's fair to say, and you're probably aware of this, Graham, but in the last 2 cycles, there has been a transition much more, and it will be true, especially in the implementation plan that's being published this year, that there's been this transition really to think about the ECVs really in a cycle context. So that's that's one way to kind of identify gaps in the existing ECV kind of landscape that exists, whereas before it was very much structured around just land, ocean, atmosphere, the individual panels that go off, do their own thing and come back. I have to say the actual process for defining ECVs is quite conservative. I mean, okay, they may seem like a lot, but I can tell you there's a lot of people that are frustrated that they don't get their own additional things in there. And then an additional point at the international level, and then I'll make one point how we apply it in the kind of the European context. But another point at the international level is there was this emphasis about 4 or 5 years ago to generate kind of these climate indicators, which are kind of derived products from the ECVs. And you see some of those if you ever go to the WMO website. I think it's right front and center on the WMO website, these climate indicators. And I think the feeling was that the data products used as input to those climate indicators are kind of like a level of priority that's slightly higher. So that was perhaps another way that they saw in prioritizing this. Then on the European implementation, and this is perhaps something that makes it a bit different to the discussion you will be having in the context of this this group, is that, of course, Copernicus is a user-driven program. So our prioritization, we take the GCOS ECV template, but then how we prioritize inside that is really depend on what our users are asking us for. We won't put everything in production if we don't have a certain user base that is asking for those. So that's perhaps a different for at least in Copernicus, maybe not so much true for the European Space Agency, but at least in Copernicus, it's really driven by what the users want. And those users could be end users who are producing their own climate services, but it could also be end use in the context of what the reanalysis system needs, or what the the IPCC community needs. So but it has to be traceable back to some specific user need or user prioritization. So that's how we do internally within Copernicus that prioritization on the products. It's basically user driven.
Yeah, thanks.
Yeah, I may compliment that. It is actually, I think, historically, So GCOS was really aiming at defining variables describing the climate system and making this more complete by adding more variables. No? But this was sometimes, it seemed maybe not even very targeted. So that's, I think, what Mark meant. And now addressing a cycle like the carbon cycle, then you immediately go to things like, okay, well, maybe we should have a fluorescence data set. No? So, and do we have good missions for that? Oh yeah, we have some research missions and planning and here and there, but we are far away from providing that continuously. No? So in that sense, this would help in driving the understanding, but they were more after climate change. And Mark has shown this super example with the CO2 monitoring with this rather contradicting requirements. No? And these missions are very so if you want to say user-driven, they're super relevant in the context of the Paris Agreement. So open source detection and verification systems, and those requirements up to now were not covered within GCOS. And of course, we have started arguing that they should cover most, and this is also true for many research requirements that originate from the WCRP or so. No? I mean, we have just an ongoing discussion within this new core project ESMO, how we can provide guidance to GCOS in terms that they can do more useful things for the scientific developments also, which is aiming then at process understanding in the context of modeling, so for parameterizations and similar things. I think we are on some road in that direction, but we have not found an agreement. But I think we're going to continue, because it's also science on how to mint requirements. So it means not just long-term monitoring requirement, but it means also a space-time scale requirements. No? So depending on the application that you want to use the data for, and this would need to be transferred into some mission measurement requirements, and that is not an easy task because that's getting very non-linear. So in that sense, this process I think is something that we could actually consider in the ESMO and involve GCOS, so to improve their processes as well. And it may also lead to some other sets of ECVs or so on, and then it will become more useful, I think.
Although, can I just mention that this approach that Tim, or this group that Tim mentioned in USGS, that is working together with NOAA, I think, on the user requirement. I've had several discussions with them lately in the context of our new knowledge center on Earth observation, and I think the approach they're taking there is extremely effective. So I think you already have some pretty good examples within the US of how you're addressing user requirements. Stacey, at some point, I see there's a lot of questions in the chat about research and operations. So maybe, I don't know if we can address that, or if you want to pass to someone else first. But
we can, and I'll come back to that in 1 second. I was going to remind participants, if they'd like to raise their hand to ask a question, please do, and I'll call on you. I did see one question for Mike Bonadonna in the chat that I wanted to ask live, which is, apart from the weather program of record and the indication of some expansion for atmospheric composition via GeoXO, do you have insight into what the next Earth science area NOAA might be interested in supporting in its portfolio of sustained satellite observations?
Yeah, I would say that NOAA is following the lead of the federal government, which is focusing much more completely on the Earth systems approach. There's been much more focus on oceanographic measurements from space than there have been in the past. We have always had them, but the emphasis is growing. Setting space weather aside, which I did mention during my meeting, during the presentation. Many of the areas that we are looking at are focused on impacts to society from climate change, so coastal inundation, hydrology, hydrological cycle. And it's not just the satellites. You know, I'm able to speak to it from the NESDIS perspective today, but looking at NOAA as a whole, there's a complete set of services to address the very wide range of observations necessary to observe the Earth system.
Thank you. I see a question from Betsy Weatherhead.
Thank you very much. It's actually not a question, it's a comment. First of all, I think these presentations have been terrific and useful, and it's great to pull everyone together. I'd like to just remind everyone that WMO is having a joint meeting with BIPM to address climate observations and the meteorological needs for climate observations in September. The abstract deadline is this week. I would love to see all of these presentations where so much work has been done be presented at that meeting. So if anyone would like to consider presenting, anyone at all, again, abstracts are due in the next couple of days. I'm going to put the website in the chat to everyone.
May I comment a little? So it's so be assured that we're gonna send one abstract. So because we need to split ourselves in different events in that week, but there will be an abstract that is basically detailing also the question you had in the chat about best practices funding for this uncertainty characterization. So I think we will hand in an abstract that shows two examples, and one is about I had a slide in this presentation which I dropped in the interest of time, which is about microwave humidity sounders, where we basically did in this fiduciary project I mentioned on uncertainty characterization of many instruments, so ATMS, MHS, the Chinese from the Fangyong satellites, and added now MSOB, SSMT2, and others. So you have all these individually uncertainty characterized and calibrations corrected as good as you can with what you know from documentation and what you can find out through a lot of radiative transfer simulation against various reanalyses. So normally we use the MERA and ERA5, of course, and the JMA reanalysis, so that you get also a little view on the model errors that may play a role in the simulations. But then we have also devised a harmonization technique for those instruments, which is based on an optimal estimation that basically takes, as you have no external really traceable reference, one reference in the series and adjusts basically all calibrations to that reference, but maintains the full error covariance matrix within that. So you have the full series uncertainty characterized, including the effects of the collocations due to this harmonization process. And this we did, and the tremendous thing that you can see there is that if you have the individual sensors, you still see in a global average sense to a global reanalysis differences of up to 4 or 5 Kelvin between that sensors. If you do the harmonization, you are down to something like 0.1, 0.2 Kelvin. And this has a tremendous effect in making data assimilation and bias correction to the model much easier, because these biases become much smaller due to the handling of the observations. And we will show that example in this workshop. There's more on visible range measurements that we also did, but then we were not so advanced in the harmonization. But you can basically do this in all spectral ranges for passive instruments. Active, we haven't tried, and that indeed, as you asked, needs more research. So on lidars and radars and these kind of measurements, we have not addressed that, and I think that we'll probably need another research project to do this.
Jörg, I really look forward to us talking more. I think your insights on how much data are needed in order to get information down that low will be particularly critical. When you have an abundance of information, then sometimes those techniques are incredibly powerful. But when there's a sparsity of information, we're a little trapped.
Yeah, a little, but we found, so as in particular, so ECMWF and the reanalyses, so they are, of course, so we saw that on one of the slides, so they tried a century reanalyses, and of course with cellular record, we try to go back as far as possible. So we have started now analyzing very old instrument data together with other institutions in Europe, like the THIR, so Nimbus 1 to Nimbus 4, SSH, so very historical stuff. And the first step that we always do in getting a handle on the quality of this is to establish a forward radiative transfer module for those. And then if you do that, then you have actually means to compare that and to see a lot on the instrument deficiencies if you compare that with a reanalysis directly. So it's not the truth, but it shows you a lot of systematic or kind of scan dependent errors and all this kind of stuff. No? So it's a powerful tool. And there's of course a limit what you can do with these old data, but the aim of this is basically only to make them ready to be assimilated in the model. And they have a tremendous impact because they are sparse observations. At those times, there was only one instrument flying of each kind, if at all.
Okay, as we're coming up on noon, I want to thank all of our speakers again. And I see one last question or comment. I will pass this to Dwayne.
Yeah, maybe a quick question for Jörg in particular. Jörg, a number of us are plan on going to the second climate observation conference, the one held in Darmstadt, which I think is in part supported by Eumetsat. Do you mind just giving just a one or two bullet remark on the intersection of today's discussion and that conference and what we may expect?
Yeah, I think I'm not part of the program committee actually. So the conference is, I think it's between the 17th and the 19th of October, which is a Monday to Wednesday in Darmstadt. And I think the abstract deadline has already passed, and I think they stitched together the program. But there is a web page. I could just, you may see it already. And so the program is, I think, GCOS, of course, will present us the new implementation plan. And if you had a chance in participating in the review of that implementation plan, which I think was also ending early June, there are a lot of actions also for the satellite agencies, and many of those point to the matter of continuity and gaps that have already materialized, like in limb sounding and all this kind of stuff, and asking the space agencies, often represented to the working group climate that Jeff and Wenying were talking about, in initializing actions on how to close it. No? So they expect international coordination. And I think there will be basically all the agencies who are probably participating in this meeting, and one can then discuss that. But I haven't seen any real deep program, how that will be arranged, and if this will be only presentations or also a lot of open round tables or so. I don't know how it will be staged up. No? But it's mostly about the implementation plan and what can be done on the actions that are in this plan. And there's a lot of in situ observations as well. No? So this covers the whole ballpark of climate observations.
I think specifically on Graham's question before on prioritization of the ECVs and things, that will be you'll probably find a lot of discussions around that. Yeah.
Yeah, that's also true. And so scientifically on this is, I mean, one part of the prioritization is the space segment, and there you would probably maintain capabilities basically for all measurements that lead to all these ECVs. But then there's a lot of funding also involved in producing ECV data records. And there you could probably start prioritization depending on what you think is the best system to produce a data record. You know? And I think we can see that data records at interfaces like so air-sea interfaces, ice, atmosphere interfaces, they remain pretty important. No? So sea level, sea surface temperature, and these kind of things. And everything that's not really well modeled in the climate or weather prediction model also remains very relevant, where you would really do the full retrieval thing and produce it. But then if it comes to temperature fields, then I'm not so sure anymore. No? So if things like reanalysis already outperform data sets that we produce, no? So there's a lot of potential duplication. And in that sector, one could probably think about prioritization. But one needs to be very careful in that, you know, that one don't destroy the good, because just by creating more efficiency and save money or so. No? But this is probably a way how one can make this whole system a little leaner and use the right tool to derive the right information for an ECV. No?
So I gather we're about to end, Stacey?
Yes, I just wanted to thank all of our speakers yet again and remind participants that we will be posting the video from all of today's symposium to the websites that are shown on the screen here. And with that, if I could ask Wing Z to please stop recording. And again, thank you everybody for attending, and thank you again to our speakers.
Thanks, Stacey.
Thank you, everybody.